March 1942. A military testing facility outside Tokyo. Captain Takeshi Yamamoto stood in the harsh sunlight watching acetylene torches cut through the hull of an M3 Stuart light tank that had been captured intact during the Philippines campaign 2 months earlier. The American vehicle sat on blocks in the center of the proving ground, its olive drab paint scorched where Japanese engineers had marked cut lines across welded seams. Yamamoto had spent 15 years studying armor metallurgy, and he understood what the Imperial Japanese Army hoped to find: weaknesses in American design, construction shortcuts taken under wartime production pressure, evidence that mass manufacturing sacrificed quality for quantity. The cutting torch hissed through the first weld seam, a vertical joint connecting the hull front plate to the side armor. When the section fell away, Yamamoto moved closer to examine the exposed metal. What he saw contradicted every assumption about American industrial methods. The weld penetration was deep, uniform, and showed no porosity or slag inclusion. The heat-affected zone was minimal, indicating precise control of welding parameters. He ran his finger along the fusion line, feeling smoothness that suggested machine consistency rather than human variation. 3 more sections were cut and examined that afternoon. Every weld showed the same characteristics: factory-level precision, uniform penetration depth, metallurgical properties that matched or exceeded the base armor plate. Yamamoto's preliminary report would acknowledge what Japanese heavy industry couldn't replicate under wartime constraints: that American welding technology and quality control were years ahead of what Japan's factories could produce, and that the M3 Stuart's construction precision represented an industrial capability the Imperial Japanese Army had no immediate means to match. Chapter 1. The Capture. 2 months earlier, on January 7, 1942, Lieutenant Ben Morin sat in the commander's position of his M3 Stuart light tank outside Manila, watching Japanese infantry advance through rice paddies toward the American defensive line. The Provisional Tank Group had been fighting delaying actions across Luzon for 3 weeks, and Moran's Company A was down to 11 operational Stuarts from the original 17 that had landed in the Philippines in September. His tank, number 41, nicknamed Georgia Peach, was running on fumes, literally. The fuel gauge showed empty, and regiment had reported no resupply coming. When the Japanese came within 500 yards, Moran ordered his gunner to fire. The M3 Stuart represented the most modern armor the United States Army possessed in early 1942. Weighing 14 tons with armor ranging from 13mm to 51mm thickness, it mounted a 37mm M6 gun and 3 30-caliber Browning M1919A4 machine guns. Its Continental W670 radial engine could push the tank to 36 miles per hour on roads, twice the speed of Japan's Type 90 FIV Heigo light tanks. The Stuart's welded and riveted construction used homogeneous armor steel that American factories had been perfecting since the late 1930s, applying automotive manufacturing precision to armored vehicle production. Against the lightly armored Type 95s that Japanese forces deployed in the Philippines, the Stuart was superior in firepower, protection, and mobility. But tactical superiority couldn't overcome strategic defeat. When Moran's Stuart ran completely dry of fuel that afternoon, he followed standing orders: destroy the vehicle to prevent capture. His crew placed thermite grenades on the engine deck, smashed the gun sight, and removed the radio before abandoning the tank. Morin triggered the grenades, watching flames consume Georgia Peach's engine compartment before he and his crew withdrew on foot toward Bataan. 11 other Stuarts were similarly destroyed that week as American forces fell back toward their final defensive positions. Yet some didn't burn. 3 Stuarts were captured intact when units were overrun before destruction orders could be executed. Another 4 were abandoned when crews fled sudden Japanese advances, leaving vehicles that had simply run out of fuel or suffered mechanical breakdowns. By late January, the Japanese 7th Tank Regiment had recovered 8 M3 Stuarts in various states of completeness. When Japanese tank officers examined the American vehicles, they understood immediately what they'd captured. The Stuart's 37mm gun could penetrate Japanese tank armor at ranges where Type 95 guns couldn't scratch American armor. The welded hull construction was smoother and stronger than Japan's riveted assembly methods. The mechanical reliability and ease of maintenance exceeded anything Japanese armor possessed. Orders went out from Imperial Japanese Army headquarters: transport the captured Stuarts to testing facilities in Japan and Manchuria for comprehensive technical analysis. What Japanese ordnance officers wanted to understand wasn't just how the American tanks fought. They already knew the Stuart was superior to the Type 95 in combat. What they needed to know was how American factories built armor with such precision and consistency, whether that quality could be replicated, and what the captured vehicles revealed about American industrial capabilities that Japan would face for the remainder of the war. And in March 1942, when Captain Yamamoto watched cutting torches expose the M3's welded seams in a Tokyo testing facility, he would discover that American manufacturing advantages went far deeper than anyone in the Imperial Japanese Army had anticipated. Chapter 2. Japan's Tank Problem. The Type 95. Heigo that Japanese 7th Tank Regiment crews drove into combat in the Philippines represented everything the Imperial Japanese Army understood about armored warfare in 1942, and everything they had gotten wrong. Weighing 7.4 tons with armor ranging from 6mm to 12mm thickness, the Heigo mounted a 37mm Type 94 low-velocity gun and two 7.7mm machine guns. Its Mitsubishi diesel engine pushed the tank to 28 miles per hour, adequate for infantry support, but slower than the American Stuart. Most critically, the Heigo's construction relied on riveted and bolted assembly, rolled steel plates attached to an angle iron frame using thousands of rivets that added weight, created weak points, and required skilled labor to install properly. The tank had been designed for a different war. Throughout the 1930s, Japanese armor doctrine focused on supporting infantry operations against Chinese forces that possessed minimal anti-tank capabilities. The Type 95 performed admirably in that role. Its 37mm gun could destroy fortifications and suppress infantry, its thin armor was adequate against rifle-caliber weapons, and its small size allowed navigation of narrow roads and rice paddy dikes. Against nationalist Chinese forces that rarely fielded tanks or modern anti-tank guns, the Heigo was effective enough. Japanese tank designers prioritized mobility and reliability over armor protection because their expected enemies couldn't threaten lightly armored vehicles. But when Heigo tanks encountered American M3 Stuarts in the Philippines, the design inadequacies became catastrophic. The Stuart's 37mm M6 gun-firing armor-piercing rounds could penetrate the Heigo's 12mm maximum armor at ranges exceeding 1,000 yards. The Type 95's low-velocity 37mm Type 94 gun couldn't penetrate the Stuart's 51mm frontal armor at any practical combat range. Japanese tank commanders who engaged American armor discovered their shells bouncing harmlessly off enemy hulls, while return fire punched through Japanese armor like paper. The riveted construction that Japanese factories had relied upon created additional vulnerabilities. When shells struck near rivets, the impact could pop fasteners loose, sending them through the crew compartment like shrapnel, even when the armor itself wasn't penetrated. The industrial reasons for Japan's tank inadequacy went beyond design philosophy. Japanese steel production prioritized naval construction. Battleships like Yamato and Musashi consumed thousands of tons of high-grade armor plate, while aircraft carriers demanded specialized steel for flight decks and hull construction. The Imperial Japanese Navy received first priority for steel allocation, followed by aircraft production. Land armor received what remained, which meant Japanese tank manufacturers worked with limited quantities of lower-grade steel. Welding technology that could have produced stronger, lighter tank hulls required industrial infrastructure and skilled labor that Japanese factories lacked. Riveting was labor-intensive but required less sophisticated equipment and training than precision welding. Japanese tank crews understood their vehicles' limitations better than anyone. After combat encounters with American armor in the Philippines, tankers reported that engaging M3 Stuarts directly was suicide. Recommended tactics shifted to ambush from concealment, targeting American tanks' thinner side armor at close range, or avoiding armor engagements entirely and focusing on infantry support where the Type 95 remained effective. But tactical adaptation couldn't overcome fundamental industrial disadvantages. And when Captain Yamamoto examined the captured Stuart's welded construction in Tokyo, comparing it to the riveted assembly methods Japanese factories used, he confronted evidence that the industrial gap between American and Japanese armor production wasn't merely significant. It represented a generation's difference in manufacturing capability that would shape every armored engagement for the remainder of the Pacific War. Chapter 3. The Welding Gap. 3 weeks later, on April 2, 1942, Captain Yamamoto returned to the Tokyo testing facility with a team of metallurgists and welding specialists. The captured M3 Stuart sat in the same position, now marked with dozens of white chalk circles indicating additional locations for sectioning analysis. Yamamoto had submitted his preliminary report, and the response from Imperial Japanese Army headquarters had been predictable. Verify the findings, look for construction flaws or quality control failures. Determine whether the captured vehicle represented typical American production or an anomalous example. What the headquarters wanted, Yamamoto understood, was reassurance that American manufacturing wasn't actually superior, just different. The team cut 12 more sections that day, focusing on different weld types: vertical hull seams, horizontal turret joints, attachment welds where brackets mounted to armor plate. Each section revealed the same characteristics that had shocked Yamamoto during initial examination. The weld penetration depth consistently measured 70 to 85% of base metal thickness, far deeper than Japanese manual welding typically achieved. The fusion zones showed uniform grain structure with minimal porosity, indicating precise control of heat input and travel speed. Most tellingly, the heat-affected zones, the regions of base metal altered by welding temperature, were narrow and consistent, suggesting automated or semi-automated welding equipment that maintained exact parameters across hundreds of feet of seams. American factories had achieved this through electric arc welding technology that Japanese industry couldn't replicate at scale. The process used electric current to create an arc between a consumable electrode and the base metal, melting both to form the weld joint. Controlling the arc's heat, the electrode's feed rate, and the travel speed required precision equipment and consistent electrical power. Resources American automotive factories possessed, but Japanese armor plants lacked. The M3 Stuart's hull had been welded using fixtures that held armor plates at exact angles, while automated welding heads followed. Predetermined paths, creating uniform seams that human welders couldn't match for consistency across mass production. Japanese welding methods relied primarily on manual technique and riveted assembly. Skilled welders could produce high-quality joints on prototype vehicles or small production runs, but maintaining that quality across thousands of units required industrial infrastructure Japan's steel industry had never developed. The naval shipyards that built battleships and carriers used manual welding for critical seams, accepting the labor intensity because each ship was essentially custom-built. But tank production required mass manufacturing approaches, and in 1942, Japanese factories simply couldn't weld armor plate with the speed, consistency, and penetration depth that American automotive-style production achieved. Yamamoto's metallurgist examined microsections under laboratory microscopes, measuring hardness gradients across weld zones, and analyzing grain structures that indicated welding atmosphere control. Every test confirmed what Yamamoto had concluded weeks earlier, but hadn't wanted to formally acknowledge. The M3 Stuart's construction quality represented systematic manufacturing capability, not exceptional craftsmanship. American factories were building thousands of tanks with welding precision that Japanese facilities achieved only in laboratory conditions or prototype production. The gap wasn't in knowledge. Japanese engineers understood welding metallurgy as well as Americans. The gap was in industrial application, the ability to maintain laboratory-level quality while producing vehicles at automotive industry speed. On April 15th, Yamamoto submitted his final report to Imperial Japanese Army Technical Bureau. The conclusion was unavoidable and professionally humiliating. American welding technology for armored vehicle production was years ahead of Japanese capabilities, achieved through industrial automation and quality control systems. Japanese factories couldn't implement under wartime resource constraints. The report recommended studying captured American welding equipment, if any could be obtained, investigating whether semi-automated welding could be introduced for new tank designs, and, most significantly, acknowledging that riveted construction methods Japanese industry relied upon produced heavier, weaker vehicles than American welded armor. But recommendations meant little when steel allocation prioritized naval vessels, when electrical infrastructure couldn't support high-amperage welding equipment, and when the industrial base that might have closed the welding gap was already stretched beyond capacity. Building the ships and aircraft that Japanese strategy prioritized over land armor. Chapter 4. American Industrial Might. While Captain Yamamoto drafted reports in Tokyo acknowledging American manufacturing superiority, the factories that had produced the M3 Stuart he examined were already building thousands more. The American Car and Foundry Company in Berwick, Pennsylvania, had begun M3 Stuart production in March 1941, applying assembly line methods pioneered by Henry Ford's automotive revolution to armored vehicle manufacturing. Where Japanese tank factories operated like heavy fabrication shops, cutting and assembling armor plates through labor-intensive processes, American Car and Foundry treated tank production like automobile manufacturing. Precision tooling, automated welding stations, standardized quality control, and throughput measured in vehicles per day, rather than vehicles per month. The scale was staggering. By the time Japanese forces captured Stuarts in the Philippines, American factories had already produced over 5,800 M3 variants. Production would continue through 1943, ultimately delivering 13,859 M3 and M3A1 Stuarts, before the design was replaced by the improved M5. And the Stuart represented only a fraction of American armor output. Over 49,000 M4 Sherman medium tanks would be produced between 1942 and 1945, plus thousands of tank destroyers, armored cars, and specialized vehicles. The industrial base that Captain Yamamoto was attempting to analyze through one captured tank represented a manufacturing capacity beyond anything Japanese industry could approach. American factories possessed advantages that couldn't be replicated quickly, even if Japanese strategy had prioritized land armor. The United States steel industry produced 90 million tons of steel in 1942, more than Japan, Germany, and Italy combined. American factories had consistent electrical power for high-amperage welding equipment, while Japanese industrial facilities faced power rationing that made automated welding impossible at scale. The automotive industry had trained a workforce skilled in precision manufacturing and quality control, concepts that Japanese armor factories, which operated more like traditional heavy industry, had never systematically implemented. The welding technology that had shocked Yamamoto's team was standard practice in American automotive plants converted to armor production. Electric arc welding stations used fixtures that positioned armor plates at exact angles, while mechanized welding heads followed predetermined paths, maintaining consistent heat input and travel speed across hundreds of feet of seams. Quality inspectors used X-ray equipment to examine weld penetration without destructive testing, rejecting any joint that showed porosity or incomplete fusion. The result was mass production that maintained tolerances Japanese factories achieved only in prototype or small batch manufacturing. Except American factories produced these precision vehicles at automotive industry speed. The strategic implications were profound but not immediately obvious to Japanese military leadership. While Yamamoto's reports documented American welding superiority, they couldn't change the fundamental resource allocation decisions that shaped Japanese war. Production. The Imperial Japanese Navy received first priority for steel. Battleships like Yamato consumed thousands of tons of armor plate, while aircraft carriers demanded specialized construction steel. Army ground forces received what remained after naval and aircraft production, which meant tank manufacturing would never receive the resources, electrical infrastructure, or industrial modernization needed to match American methods. By mid-1942, as Yamamoto filed his final analyses of the captured Stuart, American factories were producing light tanks at rates exceeding Japan's entire annual armored vehicle output. The M3 Stuart that Japanese engineers had cut apart represented not an exceptional vehicle but typical American mass production, factory standard quality that Japanese industry couldn't replicate because the gap wasn't in knowledge or skill, but in systematic industrial capability. The automotive assembly lines, the electrical infrastructure for automated welding, the quality control systems, the trained workforce, all of these advantages existed because American industry had been building precision manufactured products at massive scale for decades before the war began. Japanese industry focused on naval construction and heavy fabrication simply couldn't pivot to automotive-style mass production while simultaneously building the warships that Japanese naval strategy demanded. And that industrial reality visible in the weld seams of a single captured tank, would shape every armored engagement in the Pacific theater for the remainder of the war. Chapter 5. Lessons Unlearned. Yamamoto's report reached Imperial Japanese Army General Staff Headquarters in Tokyo on May 3, 1942, where it was read, acknowledged, and filed alongside dozens of similar technical analyses documenting Allied equipment superiority. The conclusions weren't disputed. Senior officers understood that American armor possessed manufacturing advantages Japanese industry couldn't match. What the report couldn't change was the strategic calculus that determined resource allocation. The combined fleet required steel for carrier construction, battleship modernization, and destroyer production. Aircraft manufacturing demanded aluminum and specialized steel alloys. Land forces received what remained, and that meant tank production would continue using existing methods regardless of what captured American vehicles revealed about superior alternatives. Some improvements were attempted within those constraints. In mid-1942, the Type 97 Chiha medium tank received an upgraded armament, the 47mm Type 1 high-velocity gun that could penetrate thicker armor than the original low-velocity 57mm weapon. The modified tank, designated Type 97 Kai Shinhoto Chiha, entered production in limited numbers and represented Japan's best medium tank design. But the construction remained fundamentally unchanged. Riveted hull assembly, 25mm maximum armor thickness, manual welding fitting, critical joints only. The industrial methods that Yamamoto had identified as inferior to American mass production continued because Japanese factories lacked the equipment, electrical infrastructure, and trained workforce to implement automotive-style assembly techniques. More ambitious was the Type 3 Chi-Nu medium tank, developed in 1943 as Japan's response to the American M4 Sherman. Mounting a 75mm Type 3 gun and incorporating lessons from combat experience, the Chi-Nu represented the best tank Japanese industry could design. But production told the real story. Only 166 Chi-Nu tanks were completed before war's end, a number American factories produced in Shermans every 3 days. The Chi-Nu's construction still relied primarily on riveted assembly with limited welding, and the armor steel quality remained inferior to American homogeneous plate. Japanese engineers understood what needed to be done. They simply lacked the industrial capacity to do it at scale. The welding improvements Yamamoto had recommended proved impossible to implement systematically. Some factories experimented with electric arc welding equipment, but inconsistent electrical power, lack of trained operators, and shortage of proper electrodes meant results stayed far below American standards. The automated welding fixtures that American automotive plants used required precision machine tools Japanese factories didn't possess an electrical supply they couldn't provide. Manual welding remained the primary method, with all its limitations in speed, consistency, and penetration depth. A few prototype tanks received extensive welding, demonstrating that Japanese craftsmen could match American quality given unlimited time and resources, but wartime production allowed neither. By 1944, as American M4 Shermans and improved M3 Stuart variants poured onto Pacific battlefields in thousands, Japanese armored production had essentially stagnated. Total tank output for 1944 was approximately 400 vehicles, less than 2 days' production from American factories. The Type 3 Chi-Nu, that represented Japan's best response to Allied armor superiority, equipped only 2 tank regiments before the war ended, too few to influence any major engagement. Engineers like Yamamoto, who understood exactly why Japanese tanks were inferior and what would be needed to close the gap, watched helplessly as strategic priorities and industrial limitations made their knowledge irrelevant. The bitter irony was that intelligence had worked perfectly. Japanese technical analysis of captured American equipment was thorough, accurate, and strategically sound. Yamamoto's reports had identified the critical manufacturing advantages: automated welding, precision quality control, automotive-style mass production, systematic industrial organization. But intelligence about enemy capabilities meant nothing when domestic industry couldn't respond. American tank production continued accelerating, 49 to 234 M4 Shermans built. By 1945, plus thousands of light tanks, tank destroyers, and specialized armor. Japanese production never exceeded 600 tanks annually after 1942. The welding precision that had shocked Yamamoto in March 1942 represented an industrial gap that would only widen as American factories refined their methods, while Japanese armor plants struggled simply to maintain existing output levels against resource shortages, bombing raids, and the collapsing logistics of a losing war. Chapter 6: Pacific Armor Battles. The combat validation of Yamamoto's analysis began on November 20, 1943, when U.S. Marines landed on Tarawa Atoll supported by M3 Stuart and M4 Sherman tanks. Japanese forces defending the island included Type 95 Heigo light tanks dug into defensive positions, their crews ordered to fight to the last man. When the first engagement occurred on the second day of the battle, a Marine Stuart encountered two Heigo tanks firing from prepared positions near the airfield. The Japanese 37mm rounds struck the Stuart's frontal armor at 200 yards and ricocheted harmlessly away. The Stuart's 37mm gun returned fire, penetrating the first Hago's 12mm armor with a single round that detonated the tank's ammunition. The second Hago was destroyed moments later. The engagement lasted less than 2 minutes, exactly the outcome Yamamoto had predicted 20 months earlier when examining American armor construction. The pattern repeated across every Pacific island where armored forces engaged. At Saipan in June 1944, Japanese tank companies launched desperate counterattacks against Marine positions. Their Type 97 Chiha medium tanks leading charges that doctrine said should overwhelm defensive lines through shock and momentum. American M4 Shermans met them with 75mm guns that could penetrate Japanese armor at ranges exceeding 2,000 yards. The Battle of Saipan saw 44 Japanese tanks destroyed in a single night, June 16th to 17th, during a mass banzai charge that American armor and artillery annihilated before Japanese tanks could close to effective range. Not a single American tank was lost to Japanese armor fire during the engagement. The industrial disparity Yamamoto had documented translated directly into tactical hopelessness for Japanese tank crews. Their Type 95 and Type 97 tanks simply couldn't damage American armor frontally at combat ranges. Japanese tankers developed desperate tactics: wait in ambush positions, target side or rear armor at close range, use terrain to achieve surprise, or avoid American tanks entirely and focus on infantry support. Some of these tactics achieved limited success. At Peleliu in September 1944, Japanese tanks fought from prepared cave positions, destroying several Marine vehicles through ambush before being eliminated by infantry and armor working in combination. But tactical skill couldn't overcome fundamental material inferiority. The Philippines campaign in 1944-45 saw the largest armored engagements of the Pacific War, and the results validated every conclusion Yamamoto's team had reached. When General Tomoyuki Yamashita's forces attempted armored counterattacks using Type 97 Kai tanks with improved 47mm guns, they discovered that even the upgraded weapons couldn't reliably penetrate Sherman frontal armor. American tank battalions destroyed Japanese armor with methodical efficiency. Long-range engagements where superior American optics, gun stabilization, and armor protection made outcomes foreordained. Japanese tank crews fought with courage that couldn't change physics. American armor steel that Yamamoto had analyzed was stopping Japanese rounds exactly as metallurgical testing had predicted, while American guns penetrated Japanese riveted construction with the ease that comparative armor analysis had documented. By Iwo Jima and Okinawa in 1945, Japanese forces had essentially abandoned using tanks in their intended armored warfare role. The few Type 95 and Type 97 tanks available were dug in as stationary pillboxes, buried to turret level where their thin armor wouldn't be exposed to American fire. Even in these defensive positions, American Shermans destroyed them, systematically using high-explosive rounds and flamethrower variants that Japanese tanks, designed for mobile warfare against poorly equipped opponents, couldn't withstand. The Type 3 Chi-Nu medium tanks that might have provided better resistance never reached these final battles. Production was too limited and logistics too disrupted to deploy the 166 examples built. The welding precision that Captain Yamamoto had examined in March 1942, the deep penetration, uniform quality, systematic manufacturing control, had proven decisive in exactly the way his technical analysis predicted. American tanks built with automotive industry precision survived hits that should have been lethal, while Japanese tanks built with riveted construction and manual welding failed catastrophically under combat stress. Japanese tank crews who died on Tarawa, Saipan, Peleliu, and dozens of other islands fought knowing their vehicles were outmatched, not by better tactics or braver enemies, but by industrial capabilities their nation couldn't match. The war they fought in Type 95 Hagos and Type 97 Chihas was lost not on Pacific battlefields, but in American factories where welding quality control and mass production efficiency created material superiority that no amount of Japanese courage could overcome. Chapter 7. Industrial Victory. The story of the M3 Stuart that Japanese engineers dissected in Tokyo revealed a truth about modern warfare that transcended any single battle or tactical innovation. Industrial capacity determines strategic outcomes before the first shot is fired. In the decades after World War II, military historians studying the Pacific War's material balance discovered that Japan's defeat wasn't inevitable because of any single military failure, but because the industrial disparity that Captain Yamamoto documented in 1942 represented systemic advantages no amount of Japanese tactical skill or strategic brilliance could overcome. The welding precision that shocked Japanese metallurgists wasn't an anomaly. It was the visible manifestation of American industrial capabilities, built over decades of automotive manufacturing, electrical infrastructure development, and mass production refinement. The numbers told a story of overwhelming material superiority. American factories produced 88,410 tanks of all types during World War II, including 49,134 M4 Shermans and over 25,000 light tanks. Japanese industry produced approximately 6,300 tanks total across the entire war, with annual output never exceeding 1 to 200 vehicles and declining to 327 in 1945 as resources and industrial capacity collapsed. But the disparity went beyond mere quantity. American tanks maintained factory-standard quality across tens of thousands of units. The welding precision Yamamoto examined wasn't exceptional craftsmanship, but typical mass production. Japanese tanks showed quality variation even in small production runs because manual assembly methods couldn't achieve consistency at scale. The industrial advantages were systemic and interconnected. American steel production of 90 million tons annually provided unlimited high-grade armor plate. Electrical infrastructure supported automated welding equipment that Japanese factories couldn't power consistently. The automotive industry had trained millions of workers in precision manufacturing and quality control, concepts that Japanese heavy industry had never systematically implemented. Access to resources meant American factories never faced the shortages that forced Japanese plants to use inferior steel, simplify designs, or accept lower quality standards. And the production scale allowed refinement through iteration. Each 1,000 tanks built improved processes, identified weaknesses, and incorporated lessons that made subsequent production more efficient and higher quality. Japanese industry faced constraints that couldn't be overcome through better planning or tactical adaptation. Naval construction consumed the best steel and most skilled workers because Japan's strategy fundamentally relied on sea control. Aircraft production demanded aluminum and specialized alloys. The electrical grid couldn't support the high-amperage equipment American automotive plants used for automated welding. Even if strategic priorities had shifted entirely toward tank production in 1942, Japanese factories lacked the infrastructure, trained workforce, and industrial organization to replicate American mass production methods. Engineers like Yamamoto understood this perfectly. His reports documented not just what American industry achieved, but why Japanese industry couldn't match it under any realistic wartime scenario. The human cost of this industrial disparity was measured in Japanese tank crews who fought knowing their vehicles were outmatched. Every Type 95 commander who engaged American Stuarts understood his 37mm gun couldn't penetrate enemy armor frontally, while enemy fire would destroy his tank with ease. Every Type 97 crew that faced Shermans knew the engagement would end in their death unless terrain, surprise, or luck shifted odds that metallurgy and manufacturing quality had predetermined. They fought anyway, not because they believed victory was possible, but because duty demanded it. Soldiers fighting a war their industries couldn't win, their courage unable to overcome the welding precision, armor quality, and mass production efficiency that American factories delivered as standard practice. Captain Yamamoto survived the war and worked in Japan's post-war industrial reconstruction, applying lessons learned from studying American manufacturing methods to help rebuild Japanese industry using the mass production techniques his wartime reports had documented. The irony wasn't lost on him. The industrial capabilities Japan had failed to develop for military purposes would transform the nation's peacetime economy in the decades after defeat. But in 1942, when he examined those perfect weld seams in the captured M3 Stuart, the war's outcome was already visible to anyone who understood what those seams represented. The precision welds Japanese engineers couldn't match symbolized an industrial victory that would be won in Detroit and Pittsburgh long before Marines landed on Iwo Jima or Okinawa. Modern warfare, Yamamoto's analysis had proven, rewards not just tactical brilliance or strategic vision, but systematic industrial excellence. And the side that masters mass production at quality scale wins wars before battles determine outcomes that factory floors have already decided.